This is just going to be page 2 and 3 of your buffer and titration notes. So still buffer stuff. The top of this page just says there's 3 solution scenarios. So if you have a strong acid or base in solution, you want to know the pH of it. Pretty simple. If you have 1 molar HCl or 1 molar NaOH, well, they're 100% dissociation, so that's 1 molar concentration H plus, 1 molar concentration OH negative. You can negative log those values and get pH or pOH. If you have weak acid or base, then you do Ka equals x squared over concentration of the weak acid, or you do Kb equals x squared over the concentration of the weak base. So, which you've done a lot of. Again, sorry about the glare in the video. So you gotta do that. A buffer is going to have both things in it. So remember, our buffer equations will be concentration H plus equals Ka times the acid or the base. Okay, remember these are conjugate acid and bases. This is the Ka, obviously the acid. Or we can do that. Concentration OH negative equals Kb times base over acid. You'll get the same answer either way. Okay, you can do either one, because remember, these are conjugates of each other. So either one of those equations will work out. Sometimes it's easier to do one than the other. So when you add something to a solution, you need to figure out, does it react? Is it an acid-base reaction? Okay, or is it just 2 acids mixed together, 2 bases mixed together? Or did you add a neutral salt that doesn't affect pH? Okay. So if no, then do one of those. If it is, you got to do some stoichiometry, and then we got to figure out what kind of solution we have. So I got some different things here. First one wants to know the pH. If you have 1 liter, that's going to be a key. 1 liter of 0.25 molar HCl and 0.5 molar HC2H3O2. So just think about this for a minute. This is a strong acid, so if we want to get the pH of that, we can get the concentration H plus very easily. Negative log of 0.25, because that is your concentration H plus. Well, this is a weak acid, so if we want to get the pH of this, we got to do Ka equals x squared over 0.5, and that would give us concentration H plus ions. Well, this is going to be a much more major contributing factor to H plus concentration than this is. Okay, so normally when I say we have a strong acid and weak acid mixed together, we can really just ignore this concentration H plus that's being produced. It's going to be really small in comparison to this. I'll do both here just so you have seen it. But so our concentration H plus there would be 0.25 molar H plus. So the HCl is contributing 0.25 molar H plus ions. If we just negative log that straight out, we're going to get a pH of 0.6. If we do this value over here, this value is 1.8 times 10 to the negative fifth equals x squared over 0.5, cross multiply square root. Remember, x is our concentration of H plus ions, which equals 0.003 molar. And over here we had 0.25. So if we add those together, notice it didn't change much. The weak acid contributes a very small amount of H plus ions in comparison to that. We really could have just ignored the weak acid more than likely in this case. But if we do pH then equals negative log of 0.253, because that's our concentration H plus, our pH is like 0.597, basically 0.6. So there was no reaction there. You just have a strong acid and a weak acid mixed together. Not very common that we're going to do that. All right. Next one. Next one we've got still 1 liter. That's going to be key. 0.5 molar this, so there's a weak acid. And 0.5 molar sodium acetate, just like we had before. It is a buffer. Okay, so remember, the sodium ions don't affect pH. That's the conjugate base of this acid. So we're dissolving some sodium acetate in there to get the conjugate base of this acid. And notice the concentrations are the same. And it is a buffer. Okay, so now we're using one of these two. I know this K value, and I also can figure out that Kb value, so I can use either one of those. I'm going to tend to use just this one. So our Ka in this case is 1.8 times 10 to the negative fifth, 4 for that. Obviously, we could get the KB of that if we wanted to use that as well. Let's do this. So they want to know after we add this much H+. So say we're adding maybe 0.02 molar HCl. Let's do this first. Let's figure out the pH of the buffer before we add anything to it. So we can do concentration H plus equals Ka 1.8 times 10 negative fifth. And we're using this whenever we have a buffer scenario. So whenever I have a weak acid and its conjugate base, I immediately know I'm using that equation. You got to just remember that. Times the concentration of the weak acid, which is 0.5, over the weak base, which is 0.5. So remember, whenever these two things are equal, the acid base concentration are equal, H plus equals the Ka value, because these cancel. And our concentration H plus would equal 1.8 times 10 negative fifth. I'm going to negative log that value to get our pH. So our pH beforehand would be 4.74. So that's before we add anything to it. Well, now we're adding some HCl to it. So that's going to make more H plus ions. Okay, make more H plus ions, which is going to make our pH go down a little bit. But it's a buffer, so buffer resists a change in pH. Okay, so now we need to write a reaction. So our reaction is this. So we think about it. If we add H plus ions, we're adding H plus ions. We've got to think about what the H plus ions will react with. Well, H plus weak acid, that's not a reaction. But H plus with the weak base is a reaction. So we just got to figure out what the reaction is. In this case, it's going to be H plus from our strong acid plus C2H3O2 negative. This is a one-sided arrow. Okay? All of these are going to react with however many of these we need to make our weak acid. So we think about this. As we add H plus ions, we're going to use some of this. This is going to go down in value. We're going to make some of this. Okay, now we need to be in moles, not molarity. But we're in 1 liter solution, so it's pretty easy. So I'm going to do a Lyse table here. So I'm getting down towards the end of the board. Okay, I'm going to do a Lyse table here. Our concentration H plus, we're going to say initially was 0 molar before we add any of this in. This was, and again, we're doing moles now. This is 0.5 times 1 liter is 0.5 moles. Sorry, it's that. 0.5 moles, 0.5 moles. So let's think about what's happening. We added in our H plus ions, I'm sorry, not 0 molar, not what I'm thinking here. We added in 0.02 moles of H plus ions, so we'll put that in. Now think about it as stoichiometry. Okay, so now we always do stoichiometry. So we added this much in to that, which had these two things in it. Well, these are going to react, so these are going to go down. This is going to go down by 0.02 moles. This is going to go down by 0.02 moles because they're going to react off. This is going to go up by 0.02 moles. So this is being completely used up because it's reacting with the weak base to make the conjugate acid. So this is now 0 molar, although there's still going to be some H plus ions there for a reason here in a minute. 0.5 minus 0.02 is going to be 0.48. And 0.5 plus 0.2, 0.52. So this went up a little bit. This went down a little bit by adding some H plus ions from a strong acid. Now to get our pH, concentration H plus equals K acid over base. We don't have to be in molarity because they're going to be in the same volume of liters, same volume anyway. So we can just do our acid, 0.52 over our base, 0.48, times the Ka value. So our concentration H plus is going to increase a little bit. So we go H plus equals 1.8 times 10 to the negative fifth. So our Ka value of our acid. The acid value is 0.52, 0.48. So that ratio now has gone up a little bit from what it was before. Whereas before it was 0.5 and 0.5, now it's 0.52 and 0.48. So divide those, multiply by there. My concentration H plus ions is 2 times 10 to the negative fifth. Negative log of that, and I got 4.71. Sorry, you can't see that. 4.71 is the pH. If you think about that a little bit, put that down. Our pH before we added anything was 4.74. Our difference is only 0.003. So adding a decent amount of H plus ions only made the pH go down a little bit because it's a buffer. Because those H plus ions reacted with this to make a weak acid, which does not dissociate very much and make very many H plus ions. That's what makes it a buffer. Now, on the bottom of that page, I'll do another one here. I'm going to try and get it out of the glare as much as possible. All right, so pH, I'm going to change this from 1 liter. I'll change this to a half a liter, just so you see one that's not at 1 liter solution, okay? Let's change it to that. So we have, oh, sorry. Yeah, we'll keep it at that. 0.5 molar, we have the same thing. We have our weak acid. And remember, this is not affected. This is our conjugate base. This time we're adding 0.02 moles of OH negative. Okay, so let's think about our reaction now. OH negative will react with the weak acid. So we're going to say we have OH negative. Again, this is probably being added by like sodium hydroxide or potassium hydroxide. It's going to react with the acid in a one-sided arrow. Okay, it's a stoichiometry. These are going to react until all of these are gone, if there's enough of those molecules to react them off. And we're going to make more of our conjugate base. So let's do our ice table. Initial change equilibrium. We're adding in 0.02 moles of OH negative. This was 0.5 moles per liter. But we are in 0.5 liter solution now. So remember I did that in half. So we're not going to use that value. We're going to say there's 0.25 moles of that because it's that many moles per liter. So a half liter would have 0.25 moles. This is 0.25 moles. So remember, you're not doing molarity here, you're doing actual number of moles because it's a stoichiometry problem. So as this reaction happens, these are going down in value. So these are going to go down by 0.02. That'll be 0. Down by 0.02 is going to be 0.23 moles of our weak acid. This is going to go up by 0.02, 0.27 moles of our weak base are going to be made. So this went up a little bit because it reacted with to make more of our conjugate base. So I'm going to use this one now. Concentration OH negative equals Kb. Okay, now I have the Ka of this is 1.8 times 10 to the negative fifth. So my Kb value I can use. Actually, I can do it either way. So I could use my Kb of this and do this, or we can still do H plus. Let's just go ahead and still do H plus. Okay, we can do the same thing. Since we have that Ka value, 1.8 times 10 to the negative fifth, acid over base, 0.23 over 0.27. There's our moles. Now, some people always ask, why did I not have to turn this back into molarity? Well, you would divide this one by 0.5 and that by 0.5, and you're going to get the same molarity either way. So in this case, I get concentration H plus equals 1.53 times 10 to the negative fifth. The advantage of using this one is you always have H plus ions, so you can do pH rather than POH. If we do negative log of that to get our pH is 4.81. So our pH went up just a little bit from what it was originally. So when you're doing these problems, think about what you're adding. If you're adding a base, it's going to react with the weak acid and make more conjugate base. If you're adding an acid, it's going to react with the weak base and make more conjugate acid. I'll let you try the next problems.